Okay, welcome to Chapter 6. And here's where we're actually going to get to start doing some more calculations and see how these things apply and what we've learned. The first thing that we discussed when we talked about histograms, we put a count right here. And if that count was of a measured variable, then we've created a histogram, and the picture is a distribution. And the distribution could have shape, it could have subpopulations, it have lots of words associated to it. Now what's nice about this is that it describes the population you study in various ways. For example, this histogram describes what appears to be two populations within one studied population. It seems that you have two potential normal curves that have been put together, much like men and women, or athletes, non-athletes, some measured variable that's going on. But most individuals in a population have many things that can be measured. For example, your height and your weight, your age and your height, your foot size and your weight. There's many variables that can be measured. And if we measure them in pairs, then we have the potential to put a measured variable horizontally and a measured variable vertically. But when this happens, this means that we can't count the occurrence of things, but hopefully we have enough data that when we start plotting individuals as points, let's say this individual here represents a 1065. So here is a pair of values, 10 and 65, and let's pretend that 10 and 65 here, that's not too dark. Let's make it a 10-year-old and 65 pounds. So there's a dot. Now, let's have more dots be added in here. Well, these dots, each of these dots represents an individual. Now, if it turns out that the measurement isn't fine enough and two dots are right next to each other, we often might jiggle one just a teeny bit so we can see that there's two dots there, just so we're not hiding data. We're not meaning to create an illusion. What we're trying to do is simply be able to see the number of dots. Now, what we see going on here, there seems to be a relationship. There's a potential relationship. This relationship seems to be, and we were using measured age and weight here. It seems to be as you get older, you gain weight. Now, it may not be true for everyone, and it may plateau at some point, but in general, it seems there's this basic shape right there, a basic shape of the data going uphill. As age increases, you expect weight to increase. And we also have one here that seems just a little bit odd, not quite within the normal construct here. If we see what appears to be a relationship, well, there's two choices of saying what might be going on. One might be saying that these relationships are deeply rooted in each other and they may cause each other. One may cause the other. Or it might be an entire coincidence. As a mathematician, we can't study the causes of relationships. And so we're not going to tell you if anything is being caused by anything else. What we're going to tell you is that this potential relationship has a numeric value, a number R, which is called the correlation coefficient. It describes the strength of the potential relationship. And when we pick as a mathematician or anybody where we think one of them may be the influenced variable and the other one is the influencer, we say that they're special, that one is reacting to the other. We don't want to say causal because we don't see it that way. So I believe you can probably argue that as you age, that gives you time and potential and to grow and hence carry more weight on your frame, that it seems that this one seems to be the one that's creating that reaction. That's very reasonable. We don't really search for that very much as a mathematician. We leave that to other people. We could have flipped it and planted these dots like this. And here was weight, and here was age. We had that one outline, one that looked a little bit odd. We still would get a graph that looks like that, but certain people probably would argue that weight doesn't influence your age, that age influences your weight. All right, we're going to take guesses on which one influences the other, and we're actually going to start giving ourselves names for these. Right now we're being very descriptive. So the first name that we're going to do is we're going to call this a scatter plot. And a scatter plot is nothing more than the individuals you measured with at least 2 ones, and we put 2 of them into a graph. It's very nice that you tell us how many dots you have there. That's very kind of you to do. It's also very nice of you to put the units of each of the thing up here. I mean, what happens if this is month and kilograms or something? It's very, very reasonable to do that. Now, because we have choices of which variable goes down and which variable goes up, we'd like you to make a very, very reasonable guess at which one should be horizontal and which one could be vertical. The one that's vertical is the one that seems to be influenced by the other one, not necessarily caused. Now, the book has a wonderful example on this that I think makes complete sense, and that is the number of drinks and the percent of blood alcohol content. Now, it's pretty clear if you have no drinks and then it's a fully controlled experiment that you'd expect people to have a 0 there. Let's put one person who's our test control, let's say. But then we have people that have had a certain number of drinks, and maybe it was measured in milliliters, total milliliters consumed. Blood alcohol percentage is some well-known mathematical one, and now we're going to put a little shape around this. Now, I'm not really happy with the shape that I'm seeing here. It doesn't seem really tight, because I'm really convinced that the drinks are directly affecting the blood alcohol content. But you know, it could be that people have different body types, large people, small people, thin people. So this kind of like bratwurst shape is telling me it's not the perfect relation I expected. Now, maybe it could have looked like this. If it had looked like that, then this relationship looks really tight. It's more of a pencil. So this one looks kind of like a bratwurst. This one looks sort of like a pencil. So the tighter the linear shape, the more we say the correlation has to be strong. The more blob-shaped, it's got to be weak. Well, here's a real weak one. Suppose I measure 2 things and it looks like this. Well, it's kind of like throwing darts at a dartboard. It looks kind of random. So in terms of how we see these things, the thinner and tighter they are, we refer to them as a strong, and then we head towards nothing. However, all of these pictures right here kind of look like as we go to the right, we go up. We could easily have a relationship that looks something like this. As one variable increases, the other variable decreases. Take, for example, your time on vacation and the amount of cash you're carrying with you. I bet it's going downhill when you're on vacation. You're spending money. That seems like a very nice negative relationship. Oh, I used the word negative. A negative association or relationship means when one goes up, the other seems to go down. This is a positive one. As one goes up, the other one goes up. So, here's a very simple negative relationship, and that is that the age of people and the size of percentage taking a college entrance exam, let's say an SAT. Well, as age goes up, you'd expect fewer of them because it's probably mostly taken 18, 19, and 20-year-olds, so 17 in there. But by the time you get to 30, there's very few of them, so you'd expect this to happen. So there's two things we want to look at. The general shape. Is it tight? Is it kind of bratwursty or potato shaped or a pickle? Is it getting really thin? Weak? Moving towards strong. And is it going uphill or is it going downhill? Now, those of you that remember your algebra from high school, if there's a line that's going through here that seems to represent it, these lines have a positive slope. And if there's a line going here that represented it, this line seems to have a negative slope. So when we say a negative correlation or a negative association, that means the line that we're going to choose to represent it is going to have a negative slope. And if it's positive, the line's going to have a positive slope. So our goal is to create a y equals mx plus b. We're going to put x here and a y here. We're going to create a line that represents it. Now, when we have a variable that we think influences the other variable, when we get this line, we're probably going to want to put those numbers in to predict the future. And because of that, we usually put a hat on here because we'll put an x in, use our numbers n and m and b, and predict something coming out. So we'll often write not y equals mx plus b, we'll write y hat equals mx plus b. And then we can predict what things would happen using our line that represents this data. Doesn't represent it perfectly. Now that goal is called a regression line. Now a regression line, it sounds fancy, but it's nothing really, really particular. So, how can we create this type of information, and how can we learn to interpret it? Well, the first thing we're going to need to do is we're going to need to understand how we create this number r called the correlation coefficient. And we need to understand its interpretation. So let's draw a couple of pictures here, and I'll tell you what r looks like. So if all the dots are perfectly in a row, or on a different data, again, the dot in a row, this type of super strong correlation represents r equals 0. Sorry, made a mistake there. R equals 1. A perfect relationship. Now, the next picture I'm going to draw is a slightly weaker value for R. So here's a bunch of dots, and it looks fairly pencil-shaped. And I'm going to draw one that has uses a negative association. So these two pictures demonstrate a tight pencil-like relationship. These values are R equal to plus or minus 0.9 something. We don't care what this is. And we call this very strong. This is called perfect correlation. Whoops, that's a plus or a minus. That was a minus. That was a plus association. Now, as our R values drop in values away from plus or minus 1, it represents a weaker correlation. So now I'm going to draw like an R equals 0.8. And notice it's more like a bratwurst. And we call this strong. And now we'll go to a 0.7. Kind of like a pickle shape. Notice, it's very nebulous here, but one's longer and narrower, one's a little bit fatter, and one's getting fat here. And this one we call, strangely, weakly strong. Very strong, strong, weakly strong. Now, if we get all the way down to a number 0.6, it's what I like to kind of call the potato. The shape is pretty blobular. It's become like a Idaho potato when I surround it. And this is around r equals plus or minus 0.6 something. And we simply refer to this as weak. In some areas of science, we will work with data that has a 0.6 correlation and try to understand it. But most times mathematicians only like this grouping. We don't really like the 1. It tells us we should have seen that inherently, that they're perfectly related to each other. There's not a quote a relationship. It's a function that's controlling the relationship. But these other ones are how humans seem to react, and we like this group. We don't like this one so much as mathematicians. So here's what the meaning is. So once again, we've got perfect, very strong, strong, weakly strong, weak. And they use the plus or minus 0.9, plus or minus 0.8, plus or minus 0.7, plus or minus 0.6, and we don't care what the number is after. And that's just how we describe them. So that's how that correlation works. Last but not least, if it's a plus, it's going uphill. If it's a minus, the slope is going downhill. So the m, being the slope, is also tied to this number r describing the correlation. So how do we build this number called the correlation? Well, the answer is it's a fairly sophisticated math formula, and it's not terribly hard. I'm going to write it with our fancy technique. So here we go. R equals. First off, this symbol, once again, means to add up all. So we're going to add up all of the following. You're going to take your x's, and you're going to already calculated your average, and then you're going to calculate how far is my x away from the average. And then you're going to multiply it by your y, which is the second measured variable, and you've already going to have calculated its average, and you're going to calculate how far is the y away from the average, and you're going to add these all up. And when you're done with doing that, you're going to divide by 1 less than the number you've added, and now we do what's called a standardization. It's kind of like making it a percentage, but it actually only varies between 1 and minus 1. But that's what this number does. The standard deviation of the x variable and the standard deviation of the y variable. That standardization, that division, makes this thing live between 1 and minus 1. This way we get our answers. Now, most calculators have a correlation coefficient in there. I will go through it and do a calculator one and an Excel one to demonstrate how it's calculated. This can be done on a table, and the book very carefully calculates it on a table for you guys to make it work. So we're going to stop here with this correlation, and then the next thing that we're going to do after this is we're going to get a method of creating the regression line once we have this number r, and then we're going to plot it. I do want you next time to have a calculator or a Excel spreadsheet or an Office spreadsheet with you so you can do some of this work. Thanks.